Tyrus, are you ready?
Yep.
Our next speaker is Tyrus Berry. Tyrus received his PhD from George Mason University in 2013 with Timothy Sawyer. And then he spent 2 years here at Penn State as a postdoc, and then didn't like State College too much, I guess, and moved to Washington, DC, where he's an assistant professor again in the George Mason University. So I'm happy, very happy to have Tyrus again with us. Please, it's all yours.
Well, thank you. Oh, actually, I really enjoyed my time at Penn State. It's a great town. A little cold, but that's fine. So I want to talk about some perspectives on forecasting that I've been playing around with, and I apologize. I sort of planned to get more done on this project, but there's still quite a lot to talk about. So I want to build up to, we had some great talks yesterday talking about operator estimation, and I love this discussion we were just having right before at the end of the previous talk. That's sort of how I feel whenever we get into these machine learning talks. It's just, there's so many interesting things happening, and it can be very, frustrating to try to understand, what the causes are. But so I want to start at the very beginning and start with just a deterministic forecasting problem, simple autonomous discrete time forecasting. And essentially we're just trying to learn, this map F, right? That takes us from the current time to the next time where this is some state. And so we can really think of this as a regression problem. So this is perfectly suited to sort of machine learning type algorithms as they're sort of presented to us from, the applied side. But already there's sort of an interesting dichotomy that emerges, which is that there's two paths that we can take. If we want to forecast forward several iterates in time, we can either learn the one-step function and then apply, so this is the true one-step function, we have some approximation of that, and then we can apply that over and over again to get forecasts into the future. And so you can see that what's going to happen is, as we sort of accumulate errors, the true state and our state will sort of go together for a while and then start to diverge, and then eventually, potentially be doing completely different things, especially if we have a chaotic system. Alternatively, if we want to forecast multiple steps forward in time, we can take the nth iteration of the true map and we can try to approximate that. But that has its own, sort of complexities, because, if this is, we know, like, if this is a chaotic map, we know that when we start iterating it, even though F is nice and smooth, high iterates of it can be quite complicated. And so typically when we're doing these kind of approximations, we're going to be doing some kind of regularization or some kind of projection into a space of smooth functions. And so we, this might be a nice smooth function that is well approximated in our hypothesis space. But when we take a high iterate of it, now it's sort of not so well approximated. But actually what ends up happening is that it sort of ends up giving you something like, for most typical methods, it ends up giving you something like a mean forecast. And so basically, whereas, the other, this iterative forecast will give you sort of two dynamical systems that eventually sort of are independent of one another. The direct forecast will sort of go towards the mean, whereas the truth keeps going around and following the dynamics. Your forecast eventually stops or starts doing something simple. So there's sort of a characteristic behavior. So this is just some example of what the forecast skill looks like on L63 for these different methods. So here I'm starting with sort of a noisy initial condition. And so this red curve here is the direct forecast, which doesn't have as much skill in the short term. And then in the long term, it sort of goes to a constant. So this dotted line here is the same as if you were to just predict the average of the dynamical system. So in the long-term forecast, the direct forecast does something similar to predicting the average. In the short-term forecast, the iterative does much better, interestingly, even though we started with this, we don't start with the true initial condition, we start with a slight perturbation. And so, but in the long-term forecast, you can see it does sort of worse than predicting the average, because you have these two independent things going around. And of course, your RMSE will always be best if you predict the average versus predicting something random. And so what we want is sort of a probabilistic, or I want to argue sort of as we go forward that a probabilistic forecast can kind of cut the difference between these two and sort of get most of the benefits of the short-term iterative and also sort of be consistent in the long-term forecast. This trade-off can be more significant on other problems as well. I do want to point out briefly that you will see recently some forecasts using the iterative method that I've been studying as well, where you can get really, really good skill far out into the future. And I just want to point out one slight, caveat to those methods is that they use the true initial condition. Okay, so that's sort of a big assumption, is that you have the true perfect initial condition to 16 significant figures available. So once you take those methods, so this is the iterative forecast, once you add a slight perturbation to the initial conditions. That's one minor thing. But okay, so sticking with the deterministic forecast, we're treating it as a regression problem. Already, so there's sort of several methods that we could take to try to approximate and learn this function. And so sort of a classical method would just be, and I just want to sort of say that they all have some similarities to them, although they have their differences as well. So sort of a classical method would be to do a local linear regression, where you take the function and you try to approximate it linearly near x. So xj would be one of your training data points, and x would be some new data point where you're trying to extend the function. And so essentially we're sort of looking at x near a training data point and trying to interpolate linearly implicitly using the derivative, even though we may be estimating it from data. So that's the idea of a local linear regression. Kernel regression, or this is very similar to what happens in diffusion maps if you do the Nystrom extension, if you're familiar with that. I'll be talking about diffusion maps later. So a kernel regression has this sort of form where, again, we take our new data point, our new point of interest, and we compare it to training data points. And so we're looking at some measure of proximity here. And then, rather than just using sort of one or a few nearby neighbor points, in theory, we're using all of them, and we're fitting some function c where, so basically we're trying to build up the function f out of a bunch of bump functions. So h here is some bump function, and we're building it out of bump functions that are centered around the training data points. So again, we're sort of interpolating locally from nearby training data points when we go to evaluate this on a new function. And we could play around here with, what norm we're using that could vary based on the density or something like that. So I put that in to try to compare a little bit to neural networks. So if you look at a neural network, typically it sort of has a similar form. This is a one-layer network. So you have a linear combination of h functions, but h's are now sigmoids instead of bump functions. So that's one very significant difference. Another very significant difference is that there's, this a you can sort of compare to this a in the norm here. And this is your input point. And so typically it's written as sort of an affine transformation of the endpoint. And so I just want to make the point that if you take this b constant, this bj constant, and you write it as a transpose times some xj tilde, where x tilde lives in your data space, you can think of the b's as sort of representing pseudo data points. So they're not actual training data points, but so because the b's and a's are learned from data, in some sense, it's like having an artificial data point that you're comparing your input to. Okay, and presumably these artificial data points would live near the training data, but who knows? So there's a lot more freedom going on here, and of course, you're doing a sort of nonlinear optimization as well. Whereas typically in these kernel regression problems, you only fit the CJs, and these A's are sort of tuned somehow automatically from the data. It's typically not an optimization problem inside of the nonlinearity. But so there is this sort of superficial similarity, at least, that in each one we're sort of comparing the input to something like a nearby training data point. Of course, then things can get a lot more complicated. When you do deep networks, you can start to compose these things. And then reservoir computers are actually a little bit simpler, where you fix everything inside the nonlinearity beforehand and only fit the C coefficients. So that's actually even more like kernel regression. But probably the biggest difference is the difference between bump functions and sigmoid functions. So I just want to real briefly compare on a sort of a interesting problem, just to show sort of how this can affect things. So here's a sample data set just in the plane. So these are training data points, and they're colored according to a function that I want to learn. And that function happens to only depend on the theta angle component. So it has no dependence on R, but I've added a little bit of noise to it as well. So it's just sine of 6 theta. That's the function that I want to learn. And so, so here what I'm doing is I'm showing that function interpolated to the entire plane. but I've localized it. So I've multiplied it by something that decays away from the circle. So I'm really only focusing on what's happening to the function near the unit circle, which is where I have training data, right? And so the question would be, well, what the heck's happening far away, right? Because I've extended this function to the entire plane. So first, I just want to show that you can use the Nystrom extension based on, this is essentially the kernel regression that we were just talking about, which is based on bump functions. Okay, so you can, build a good approximation to this function near the training data set based on bump functions. This is a sort of two layers of sigmoids, 2-layer neural network, a deep network, also trained on the exact same data, and also does very good job of approximating the function near the data points. And so it's interesting to look at what happens away from the training data. So I say true function, that's a bit tongue-in-cheek. I mean, who knows what the true function is away from, who's to say what the true function really is away from the training data points, right? But you can imagine this is sort of the simplest possible function, the simplest possible extension of this function to the plane. And that's essentially what diffusion maps finds, or something like that. So it sort of just extends it out, and it doesn't do any kind of trend following or anything like that. And because it's bump functions and they sort of decay away from the data point, it's basically not able to be too creative away from the data set. So you can see that as a good thing or a bad thing when you compare it to the neural network, which can kind of do all kinds of things away from the data set. On the other hand, you don't sort of have so much control over what it's doing. I mean, this is trained using standard methods of stochastic gradient descent. So it's sort of interesting. So that's just sort of a little bit about regression perspective. So my understanding of this problem is evolving, and so I just wanted to sort of share this to start with. But my main point that I want to get to is that this sort of treating it as a regression problem is not the whole story. So immediately, one of the first things that you want to ask when you're doing forecasting is, can I do uncertainty quantification? Okay, so I still am sticking with my discrete time deterministic problem for now, but now instead of having a deterministic, known perfect initial condition, instead I've got I know that my initial condition is sampled from some distribution. So my data is now a probability distribution about the initial condition rather than the true initial condition. And so when you ask about uncertainty quantification, you're really asking, how do I move a probability distribution forward in time? And at least for discrete time deterministic dynamics, that basically just amounts to you want to learn this operator, which takes the probability distribution and composes it with the dynamics, precomposes it with the dynamics. So I want to say, of course, we can, so in the context of UQ, we can still treat this as a regression problem in the sense that we could just learn F from the training data, and then we could apply all kinds of UQ methods. So pick your favorite. You could build an ensemble and forecast them forward and do Monte Carlo or do some kind of polynomial chaos expansion. So that's one option. But I just want to point out, so at this point, we have the option to consider treating this as a regression problem. But we do have another option as well, which is to sort of move from trying to learn F to trying to learn script F, the operator. And so the nice thing about script F, of course, is that it's a linear operator, right? Function composition, precomposition is just linear. And so if we decide to go with option 2, then a natural way to go about that would be basically to pick a, it's a linear operator. Let's pick a basis and let's write the operator in the basis. And of course, we're going to have to implicitly, when we do that, we're going to be picking a function space. We're going to have to truncate this this operator onto a finite dimensional matrix when we want to do the forecasting. And so implicitly there, again, we're choosing some sort of regularization. And so there's all kinds of interesting issues that I think are being analyzed right now in the literature. These are sort of issues that are being addressed as we speak. And I'm not going to get to all of them. But the one issue that I want to talk about first is, which basis should we pick, right? So that's the one issue that I want to sort of mainly address in this talk. And at least for a large class of stochastic differential equations, I'm going to argue that there is sort of a natural choice of basis functions. Okay, so this is the idea, right? We've got our linear operator, we pick a basis, we'd like this to be sort of ideally an orthonormal basis, with respect to a natural inner product. We'll get to that a little bit more later. And so then we'll collect this matrix representation of our operator. And what's really nice is that if we're talking about a dynamical system, we can estimate this in the Monte Carlo sense, basically just by averaging over the data set. And at least on the data set, if our data set is a realization of our process, if it's the time series, then the F map is just the map that gives you the next element of the time series. And so, so this is how you would end up estimating these coefficients, just by evaluating one of your basis functions at xk, and the other basis function at xk plus 1. So that's the fancy F map there for you. Okay, so that's going to come up several times more. So that was still deterministic forecasting, and so even if you go beyond just basic prediction and you want to do uncertainty quantification, already you can start to think of it as an operator estimation problem. But now when you get to stochastic forecasting, you really have no choice, I think, but to think of it as an operator estimation problem. So now we've got the stochastic map that takes us from time k to time k plus 1 that depends on some random variable omega k. And now this really is, we don't want to just, you know, average this over omega k and get a deterministic map, right? That's not really going to tell us what we want to know. So what we really do want is this push forward operator that pushes a probability distribution forward in time. And to do that, we sort of have to precompose with the dynamics and then average that over all possible realizations of the noise. And that's really just not the same thing as averaging over the noise and then pushing forward. Okay, so at this point, we really do need to start thinking about operator estimation, as a lot of people are already talking about. And they're talking about this in a much broader context. I'm just focusing just on you know, prediction, forecasting, in dynamical systems. Okay, so we're back to you know, so if you want to do UQ, then this is an option for you, and if you want to do a stochastic forecast, then I claim really you need to be doing operator estimation. And so this method of picking a basis and representing your forecast operator in a basis as an option is a natural way to go about that. And so then we want to consider the error sources. Okay, so we've got this estimator for entries in our, you know, finite dimensional representation of our operator. And so naturally we want to think about what's the bias and variance of this estimator. And then something that I haven't really got to, but we really should be thinking about is truncation. Okay, so how does the choice of basis affect, you know, the truncation of this? That's something I'm not going to be able to talk about, but I will be able to talk about sort of bias and variance for a large class of dynamical systems. Okay, so what I want to argue is that first we want to choose a basis that respects the certain inner product, and that inner product should be an inner product with respect to the invariant measure of our dynamics. And so that's the first point. And if you do that, basically you'll have an unbiased operator. If you have an orthonormal basis with respect to the measure of your dynamics, you can pretty much have an unbiased operator or an unbiased estimator. But then the more interesting issue is how can you minimize variance? And so I want to argue that for a large class of dynamical systems, that comes down to you want a nice smooth basis. But then of course that could be compromising you in terms of truncation. And so not much to say about that so far, but I will talk about bias and variance. Okay, so how do we go about finding this nice basis? Well, we're going to use this manifold learning tool, diffusion maps, if you're familiar with that. And I'll have a slight twist on it that we've learned, but it's essentially the diffusion maps algorithm. And so the idea is we want to learn a manifold. Well, what do you mean by learn a manifold? If somebody gives you a bunch of data points on a manifold, it turns out that a good way to think about learning the manifold is to learn the Laplace-Beltrami operator that does actually encode all the information about the manifold, as I'll come back and talk about later. But the really sort of nice analysis piece of why this is a useful tool is that the eigenfunctions of this operator give you an orthonormal basis for the natural function space, or at least the function space you want to start with, which is L2 functions on your manifold. So you get an orthonormal basis, that's great. But not only that, they're also a really smooth basis. So these sequentially minimize this roughness functional, which is the Dirichlet energy on your manifold. So this is essentially the Fourier basis on your manifold. And so it's a really awesome analytical tool if you're going to do an analysis on a manifold. And so if you're going to do analysis on a data set, you know, that's approximating a manifold, it sort of makes sense that this would be a good thing to go for. And so this can sort of serve as the foundation for wavelets and Sobolev spaces and everything that we classically like to study on manifolds. So I want to present maybe a slightly different version of diffusion maps than you're used to. So this is one that I call the conformally invariant diffusion maps. And the difference is that we're going to do a slightly different normalization than they do in diffusion maps. If you're familiar with diffusion maps, then this is it's somewhat equivalent to using the alpha equals 1/2 normalization, because we want to get a Laplace operator that we want to get a basis that's orthogonal with respect to the sampling measure. So the idea is we have some data sampled on our manifold embedded in a potentially high dimensional Euclidean space. Of course, we need to assume that we have, a fairly dense sampling, and so probably we're going to need a fairly low dimensional manifold. So there is a cursive intrinsic dimensionality here. It doesn't depend on the dimension n, but it does depend on the intrinsic dimension of the manifold. And then our data may not be sampled according to the volume measure, but it may be instead sampled according to the invariant measure of the dynamics, which we'll call PEQ, when we write it with respect to the volume measure. So this is the sampling density, essentially, of our data. Okay, and there's no reason to believe that that would be, distributed according to the volume measure, so that we introduce this PEQ measure. So what we're going to do that's slightly different from diffusion maps that I found is really a big boost, is to, instead of using distances, we're going to use this continuous k-nearest neighbors dissimilarity. So the idea here is we take the distance between two data points and we rescale it by taking the distance between I and its kth nearest neighbor, and then the distance between j and its kth nearest neighbor, and then we take a geometric average of those two. And so the reason that I find this is really helpful is what's about to happen in diffusion maps is we're going to take this distance and we're going to shove it into an exponential function, an exponentially decaying function. And so if you think about a data set that maybe has big differences in sampling density, so some regions of data where their data are very tightly clustered together and other regions where they're much more spread out, that would mean that there would be very large variations in sort of the distance to the nearest neighbor in that data set. So what that means is that when you plug that into an exponential map and you try to find a single bandwidth parameter delta that sort of does a good job, you're going to have a really hard time, because let's say you've got distances, to nearest neighbors that are on the order of 1, and then other distances that are on the order of 100, right? It's going to be hard to find a delta that can sort of capture both of those simultaneously. But when you take those distances and you rescale them by distances to the nearest neighbor, and there's a couple nice things going on here. This is a symmetric rescaling, and then also because it's a geometric average, it's unitless. So this sort of gets all of those distances to nearest neighbors on sort of on the same order of magnitude. And so that means when we stick them into the exponential kernel, we can much more easily find a single delta parameter that's going to work well. Now, so this is what we call a variable bandwidth kernel, because this bandwidth delta this isn't really constant. The bandwidth function would really be these underlying distances here to the kth nearest neighbor. Also, we do introduce an additional nuisance parameter k, but that's not too hard to tune. Now, the interesting thing is that when you do this normalization inside of the kernel, you no longer have to do the diffusion maps normalization outside of the kernel. So we've essentially taken care of the normalization inside of the kernel rather than outside of the kernel. And we found that that's a lot more robust. So, so notably missing here is, if you're familiar, is the diffusion maps normalization step. So from here, we can go directly to building the unnormalized graph Laplacian. So we take this kernels as our graph weights, and then we build a degree matrix, and then we build the unnormalized Laplacian, graph Laplacian. And so we can prove that that converges at least pointwise, and we're working on spectral results. So that converges, this unnormalized graph Laplacian will converge to the Laplacian on the manifold with respect to this Riemannian metric G hat, where G hat is the Riemannian metric that you inherit from the embedding, rescaled according to the density to a certain power. And so this is what gives us the conformal invariance, because if you take the data set and you apply any conformal transformation to that data set, that will do two things. It will change the geometry of the manifold, and it will also change the density. And those two terms will exactly cancel out in this formula. And so that's why this is a conformally invariant choice of Laplacian operator. So you can do this in different ways, and you could get the Laplacian with respect to the the inherited metric or various other metrics, but this is a particularly nice choice we found. Okay, and so then you solve an eigenproblem, and that gives you an approximation to the eigenvectors. And so this is where you need the spectral convergence result, and that's something that a lot of people are working right now on, and we are as well. Okay, but the goal here basically is to estimate the Laplace operator with respect to a certain Riemannian metric and get the eigenfunctions, right? And those eigenfunctions are going to give us our basis. So, so these are what the eigenfunctions look like, and like this is on an interesting manifold with boundary. And the first eigenfunction is always the constant function. That's the smoothest possible function on any manifold. And then these are actually produced from a data set using the algorithm. And then after that, you start to get sort of your sine and cosine functions, and then sine and cosine of higher frequencies. So these are the Fourier basis functions that are becoming more and more oscillatory. And I should point out that recently we have extended this result to manifolds with boundary, except that the result is no longer true in the strong sense, but it's still true in the weak sense, where this L is the graph Laplacian matrix that you construct. So if you compute this H transpose LF, this inner product, that's the Dirichlet inner product on the manifold. That's what we're able to show. And so that's a result of Ryan Vaughn, who recently graduated from George Mason. This is sort of a more technical version of that result. But there is a sort of a weak sense consistency even on manifolds with boundaries. That's why I'm showing this. But what's really cool is when you go to these higher frequency Fourier functions, right? These are the generalizations of sine and cosine. They start to have really interesting structure, right? That respects the geometry of the manifold in a cool way. So these are your Fourier functions on some kind of data set or manifold that you can get from this conformally invariant diffusion map. Okay, so again, the overview so far is, we want to do kind of either UQ or stochastic forecasting. That means we need to be doing operator estimation, or at least we probably want to be doing operator estimation. And that in order to do that, we need to pick a basis. Okay, and so I want to argue that that this diffusion maps or conformally invariant diffusion maps gives you a good basis for forecasting. So here's a class of stochastic dynamical systems, SDEs. So this is taking place on a manifold. So this would be, Brownian motion on your manifold. And these are unknown, so that you don't know what this equation is, but you're assuming that you have a time series that is sampled from a realization of this process. And you're not really interested in the equations, but you're interested in predicting it. So we're not trying to learn this equation, but we do need to assume that that equation exists in the background in order for this to be the right choice of basis. Okay, so then if we want to take a probability distribution and forecast it forward in time, we can say a little bit more about that now for this specific problem. So that forecast problem is given by a PDE, and we've seen lots of people solving PDEs with machine learning. So this is only one very specific PDE, but so this is sort of fits into that framework. And so this PDE has a nice semi-group solution, at least for, a reasonable class of these dynamical systems. And so this is that forward operator that we were talking about earlier that's pushing the density forward in time. And so that's what we're interested in learning for this class of systems. Okay, and so because we have an SDE, we can actually start to say a little bit more. So when we talk about this, what we're calling the shift map, if you like, it's sort of the Koopman operator, but for a stochastic realization of a stochastic process. So the Koopman operator takes a function f and it maps it to a new function whose values are just shifted down the time series forward by 1. And so that's basically telling you what's the value. So the shift operator of a function at time I is the value of the function at the next time in the realization of your time series. And so that's given by the adjoint of your forward operator applied to that function, evaluated at the current time, plus some error term. Okay, and so you can derive the error term from Ito's lemma. Okay, so what this tells you, and this is why it's important to talk about a specific type of process, is that first of all, the expected value of the shift operator, so the expected value of these terms all turns out to be 0. This because it's a stochastic integral, and this because this is a centered process, this B operator. And so, so the expected value of the shift operator is just the adjoint of the push forward operator that you want. Okay. And so that means that these are the error terms that are going to define your variance. So first of all, this is going to be unbiased as long as we have a basis that has the right orthogonality properties that we need. So we're going to have an unbiased operator. And so then our variance is going to be dominated by the stochastic integral term. Okay. This is a higher order term. And so this is sort of order root tau, where tau is your time step. That's going to dominate your error term. And so what's really interesting, of course, is that in order to make this, you don't have control over B. That's the unknown diffusion tensor of your stochastic system. So the only thing that you can choose is you can choose Fs, right, that try to make this gradient small. And that's how you can try to minimize the variance on these estimators. So this is the idea of doing this, sort of forecasting just laid out in a diagram. So you've got some probability distribution that you want to forecast forward in time to time t plus tau. And in order to do that, you're going to take that probability distribution and represent it in this basis. Okay, so we're going to choose these basis elements to be the eigenfunctions of that conformally invariant diffusion maps Laplacian. Okay, so we get a bunch of coefficients, okay, and then in order to forecast the coefficients, all we have to do is multiply them by the matrix representation of our operator. And then once we forecast the coefficients, then we can just reconstruct the future probability distribution. And so in order to estimate the coefficients of the operator, we're going to use the shift map. And so this is that, again, that Monte Carlo estimator using the shift map. And so as long as these phi j basis elements that we chose are orthonormal with respect to the invariant measure of the dynamics, then so over the long term, this is going to converge at least weakly to an integral with respect to the invariant measure of the dynamics. And so that means that that we will have an unbiased operator due to that orthogonality property. So that means the expected value of our estimator will be the true entry in the matrix representation of the forecast operator. And then the error is given, the dominant term in the error is given by that stochastic integral term. And so that ends up being, from this stochastic integral term here, we ended up getting the gradient of the basis functions that we chose with respect to that geometry measured with respect to the invariant measure. And so we can minimize this by choosing the basis functions that minimize the Dirichlet energy. And that's exactly what the conformally invariant diffusion map does. So that's the sense in which we can build an optimal basis for this class of dynamical systems or stochastic systems. All right, so we choose those eigenfunctions to minimize the error, and we can use the conformally invariant diffusion map algorithm, at least when we have sort of a low enough dimensional manifold that that it's well sampled to approximate those eigenfunctions. All right, so the way this works, so I'm going to immediately violate all my assumptions because I assumed this was taking place on a manifold. But the point is that, the algorithm that this is based on, the conformally invariant diffusion map, can be applied to any data set. So even though proving optimality requires an assumption of a stochastic differential equation on a manifold, we can still apply the algorithm on something like the Lorenz attractor. And so these are the eigenfunctions that you get on the Lorenz attractor. And then you take the shift map and you build a matrix representation of the shift map in this basis of eigenfunctions. And so that gives you this matrix here. So this is the shift map represented in the basis. Okay, and then you can do the diffusion forecast and you can predict the mean. So you're actually forecasting a full probability distribution. And I'll show you just a minute in a video what that looks like. And so when you forecast for probability distribution in the future, you can get the mean, but you can also get the variance or other estimator, other kind of error estimates if you like. And so the blue curve here is the RMSE of the mean of the forecast, and it sort of tracks well. So the gray here is an ensemble forecast using the true dynamical system. And so the blue is tracking fairly well, and but also you're getting a reasonable uncertainty quantification. So the dashed line here is the variance that you would estimate from forecasting the probability distribution forward in time. Okay, so this is what it looks like. So here's the diffusion forecast. This is a probability distribution initialized on the Lorenz attractor, and we're going to push that forward in time using the diffusion forecast. And then here's an ensemble sampled from the same distribution that are going to be forecast forward in time using the true dynamical system. Oops. So let me back it up there a little bit. So if you just run it forward in time, you can really capture quite a lot of information about the distribution. And you can see, so what's going on here is in the background, you can see these are the training data points in light, the small blue dots. So I've got sort of a well-sampled attractor going on here. But there's a lot of interesting structure in the distribution, and it's fairly well captured in the diffusion forecast. And then if you keep running it forward, you can see even really far forward in time, you can capture some of the course structure of what's happening in the distribution. And so that's also sort of illustrated in this picture here, where, you know, these are large RMSEs, but there's still information there about where you are on the attractor. Okay, so let me skip forward a little bit here. So of course, the one caveat is all of this is subject to the curse of intrinsic dimensionality. So using diffusion maps, we avoid the curse of extrinsic dimensionality, but we still have the curse of intrinsic dimensionality. So we still need data that grows exponentially in the dimension of the manifold. I want to skip forward a little bit here because I want to talk about sort of another way that you can use sort of use these this basis. Okay, so again, I've been arguing for this diffusion maps basis of eigenfunctions of the zero Laplacian, and talking so far about representing an operator, a forecasting operator for a stochastic dynamical system. So I was working with Demetrius on doing forecasting for deterministic systems, and there the idea, you know, again, in discrete time, you're interested in learning a map, but in continuous time, you're really interested in learning a vector field. And so we were thinking about how can we represent a vector field on a manifold, or how could we smooth or regularize a vector field that we're trying to learn on a manifold. And so that really got us into thinking more about the exterior calculus on the manifold. And so I mentioned earlier that if you know the Laplacian, technically you know everything about the manifold, because the Laplacian will help you recover, from the Laplacian you can recover the Riemannian metric on the manifold, and from the Riemannian metric you can build the entire exterior calculus on the manifold. So the exterior calculus is basically the calculus of differential forms, and one of the key elements of it is what are called the K-Laplacians, and these are just direct generalizations of the zero Laplacian, so the zero Laplacian axon functions. And if you think about differential one forms, those are dual to vector fields. So in the case of the one Laplacian, you can really think of that as like a Laplacian that acts on vector fields. And so it'll have a set of eigenfields. Okay, so the eigenvector fields that are basically the smoothest possible vector fields on your manifold. Okay. So, you know, I liked the zero Laplacian, so the one Laplacian seemed like a good thing to go for. And so I was really interested in trying to find these eigenfields of the one Laplacian, especially for trying to analyze vector fields on manifolds. And so the question was, you know, how can I build all this structure, right? So there's this theoretical connection that says if you know the Laplacian, you know everything, okay? And so so Demetrius and I wanted to sort of figure out how we could actually manage that, okay? And we wanted to do it in such a way that we could generalize it to arbitrary data sets. So even though, you know, we can prove all these theorems in the case of data on a manifold, we wanted an algorithm that still worked even when your data wasn't on a manifold. So we didn't want to sort of have to explicitly approximate the tangent space or anything like that would require, it would sort of only be valid when the manifold assumption was really true. Okay, so the idea was, we know that diffusion maps works really, really generally on data sets, and what it gives you are, you know, it gives you these set of eigenvectors or eigenfunctions, and it gives you eigenvalues, right? That's what you get. And so we wanted to try to build everything, the entire exterior calculus, just using those eigenvectors and eigenvalues. So here's the connection that we have. So here's the Riemannian metric. So the Riemannian metric is basically a inner product on the tangent space of a manifold. And it tells you when you have two gradient fields, so the gradient of some function and the gradient of some other function, it tells you how to compute their dot product in that tangent space. So that's what you need to specify sort of everything about a manifold, is what are all the dot products and all the tangent spaces. And so you can recover this sort of a fluke from the product rule on the Laplacian. So if you've ever seen the product rule for the Laplace-Beltrami operator, it has this grad.grad term in it. And so if you just solve for the grad.grad term, you'll get an expression for the Riemannian metric only in terms of the Laplace-Beltrami operator. So that's kind of cool. And that's what we have available for us. Okay, and so how can you extend this to to sort of the rest of the manifolds. That's where things gets a little bit tricky. And how can you do this purely in terms of the eigenvectors and eigenfunctions of this zero Laplacian? Okay, so the first thing that you could do is you could say, okay, well, let's take two vectors in the tangent space, right? Then what I could do is I could find a set of functions whose gradients are a basis for that tangent space. Well, they have to at least span, but I can actually find, if it's a d-dimensional manifold, I can find d functions, right? Because I'm at a certain location x on the manifold, I've got a tangent space, I can find myself d functions whose gradients span that tangent space. And then if I wanted to know what's the dot product of v and w, I could take v and w and write them in this basis, right? And they'd have coefficients vj and w, or vi and wj. And because I know how to dot all the gradients together, now I could extend that to know how to dot product any two vectors together. Okay, so that's great. So now I can figure out what the dot product is. I know what the Riemannian metric is in this tangent space based at x. The problem is that I can't actually extend that to the whole manifold because while at every x I can find a bunch of functions that will, a collection of d functions that will do this, it's not true that I can find d functions that will do this for every x. Okay, so I can't find d functions on the manifold whose gradients will always span every tangent space. And a simple counterexample to that is the Harry-Ball theorem. It says every vector field on a sphere has to vanish. And so at that point, I obviously won't span. So what's interesting is that even though you can't do it with D, you can always do it with 2D functions by Whitney's embedding theorem, because I can always find, again, typically we're starting with an embedding of our manifold, but I want to go back to just starting with just eigenvectors and just eigenfunctions of the Laplacian. So it's always possible to find an embedding of the manifold into 2D dimensions. But that's not useful to me because I don't really know how to find that embedding. So what was really cool for us was that there's this theorem proved in 2014 that it's actually not by us, but by somebody else, that that if you take sufficiently many eigenfunctions of the Laplacian, just the zero Laplacian, those will eventually form an embedding. Okay, and so that told us that if we take enough of our eigenfunctions, we take all their gradients, those eigenfunctions will form an embedding, and that means that their gradients will have to span every single tangent space simultaneously. Okay, but of course it's not going to be a basis, right? It just means that we're going to span. Okay, and so what that means is we can't work in the world of bases anymore. We have to work in what's called a frame. And so a frame is a fancy sort of an overcomplete set that's not too overcomplete. So what we're able to show is that if you have a vector field on your manifold, you can always write it as a linear combination of phi I grad phi j. Okay, so not just just grad phi j's is not good enough, but so these phi's are the eigenfunctions of the zero Laplacian. And so every vector field can be written as a linear combination of these sort of basic vector fields, which is some eigenfunction of the zero Laplacian times a gradient of another eigenfunction. So then we were able to prove that the collection of those phi I grad phi j's actually forms a frame. And so what that means for a frame for the space of L2 space of vector fields on the manifold, what that means is a frame is sort of like what you do when you don't have a basis. Okay, so the idea is you want to, so these are your frame coefficients. This is like taking the inner product of each of those basis elements, right? But because it's not a basis, the sum of the squares isn't going to add up to the norm. And so what I want is I want some inequalities that tell me that they don't sum up to infinity or something crazy like that. So I want to know that my set isn't too redundant. And then I also want to know that they don't add up to something too small. Okay, so this is what we were able to prove. And based on that, I think I'm running a little low on time here. So based on that, we were able to actually build a representation of the one Laplacian. Okay. Let's see. Okay, and so once we got the one Laplacian, we could find the eigenvector fields of the one Laplacian. And so these are the smoothest possible vector fields on a manifold. So here's like the smoothest two vector fields on the Mobius strip, or the smoothest two vector fields on the sphere. You can see they satisfy the Harry-Ball theorem. But our method applies even beyond manifolds because it's just purely based on eigenfunctions of the zero Laplacian that we get from diffusion maps. So we could apply this to find the smoothest two vector fields on the Lorenz attractor, for example. And let's see. So I just want to point out that there is code available for this. So we call this the SEC, or the spectral exterior calculus. And the last thing I want to point out is that we could use this to, so this was sort of our goal was, let's say we want to estimate some dynamical system, the vector field of a dynamical system. So here's the true vector field. And so then one way that you would start by estimating that is using just finite differences if you only had discrete estimates in time. And so then there's multiple ways that you could smooth that. You could try to smooth the components of the vector field using diffusion maps, right? And this is the smoothing that you get. And so you really lose a lot when you do that. But if you smooth it by truncating it in the basis of the smoothest possible vector fields on the manifold, you really get a nice representation. And so that's sort of where we were going with this as one of the applications. There's lots of other ideas floating around there, but I just want to, so I'll point you to the spectral exterior calculus paper and to my website for code and papers if you're interested, and welcome any questions. Thank you.
Thank you so much.
Okay, so I didn't see any questions from the audience.
Uh-oh.
But I have one, right?
Sure.
Can you compute covariant derivative?
Let's see, covariant derivative. No, that one's a little bit tricky. Oh, well, you can, but we don't have good error bounds on it. So yeah, so to compute the covariant derivative, you have to represent the vector field as a matrix, and then you do matrix multiplication essentially. So the covariant derivative, you typically have two vector fields, right? And so you want to compute the covariant derivative of one vector field with respect to the other, and that can be done in terms of matrix multiplication if you represent the vector fields as matrices in a certain way. But no, I think that was one thing that we're still working on in terms of how to represent covariant derivatives. So we do have a way to do it, but we don't have good error bounds on it, and it doesn't.
How expensive it is to get eigenfield of one Laplacian?
Say that again.
And sorry, how expensive it is to get eigenfield of one Laplacian? Do you have any complexity?
So so what's interesting is that in order to do this, what you do is you take the one Laplacian and so it's just like what we were doing when we were doing forecasting. Okay, so you take the one Laplacian and you represent it in this basis, right? Or this frame really of phi I grad phi j. So it's a spectral truncation of the operator, and so you can kind of choose how many eigenfunctions you want to use in that spectral truncation. Okay, so if you use a lot, then it'll get very expensive, and if you want to calculate the highly oscillatory eigenfields of the one Laplacian, then you're going to need a lot. Okay. You're going to need so that will be expensive. But if you just want the sort of the first, 10 smoothest ones, you can get away with a pretty severe truncation of the one Laplacian, meaning that you can use a really small representation. So it can be affordable if you just want a few eigenfields, but if you want a lot of eigenfields, then it will start to get expensive fast, mainly because you're going to need to resolve a lot of this operator. So you're going to need a fairly resolved, you're going to need a big basis to represent it in, and you'll get a big matrix representation.
Right. My son just come back, so, so.
I have a probably naive question. You mentioned that it's much harder to do spectral convergence analysis for the graph Laplacian to the. So for eigenvalues, you always have Rayleigh quotient characterization. And then you can evaluate this Rayleigh quotient characterization in terms of convergence, how close you are to the minimum using. So why wouldn't then kind of pointwise convergence imply, or uniform, I guess, pointwise convergence of in H1 space imply good estimates for the eigenvalues of the graph Laplacian?
Yeah.
What am I missing in this argument?
So I think there's sort of an abusive notation when it comes to pointwise. So when they say pointwise, what they really mean is that if I take, so this is the graph Laplacian multiplied by a discretization of the function, and then I evaluate, if I take the ith entry of that vector, then that will be the Laplacian of f evaluated at xi, the ith data point. So by pointwise, they really mean at a point xi, whereas I think a lot of people, when they say pointwise, they mean the points would be the functions in the Sobolev space. So this is a much weaker result than you would say pointwise Sobolev space convergence. Yeah, so basically that is the issue, is going from pointwise. What we meant by pointwise was at a point x on the manifold, this estimate holds. Okay, now as long as the manifold's compact, then you will at least have a uniform in you'll at least have uniform on the manifold with respect to x in terms of these error bounds. But basically, in order to lift that to pointwise in the sense of like pointwise on a Sobolev space, you need to you basically so these error terms here involve derivatives of f. Okay, so this is one of the things that we've got Ryan working on right now, my former graduate student. So yeah, so these error terms involve derivatives of f, and so if you work those out very carefully using partitions of unity on the manifold, you can show that that those are bounded. And so then what you need to do is then you need to pass to the completion, because these are basically, all these estimates are proven using Taylor expansions. Okay, and so in order to prove them, you have to start with f in C3 at least. Okay, so you're proving this for C3 functions, and you're proving it pointwise in the sense of you're proving it at a particular x. So you do that, then you have to show that the error terms, are bounded, which depend on derivatives. That's fine if you assume your f is, C3 or whatever differentiability you need. And so the complexity really comes in passing to the limit or passing to the completion of C3 with respect to the Sobolev norm. And so that's what we're sort of working on right now. There's a bunch of complexity in terms of like building Sobolev spaces on manifolds and exactly how those are defined. But yeah, it seems like that all will work. So I think your intuition is correct, but there's just a bunch of details that we haven't worked out yet. But you're right. Once you get pointwise with respect on a in a compact space, once you get pointwise with respect to f in a Sobolev space, then that passes to spectral convergence, I think, fairly easily. That's a good point.
Yeah, thank you. I have a couple of questions in the chat. So
sure.
So Alpha says, "Hi, nice presentation, Tyrus. In the variable bandwidth diffusion kernel with the CKNN, is the matrix K symmetric or not, or non-symmetric?"
Yes, it is symmetric. So that's the advantage of the CKNN, is because we take xi and we subtract its kth nearest neighbor, and we take xj and subtract its kth nearest neighbor. And so if you switch I and j, you're still, these two terms right here are going to switch, all right, but you're still going to have the same quantity. So it's still a nice symmetric matrix. And actually, even this unnormalized Laplacian is still symmetric. And then when you go to do the to solve the eigenvalue problem, you can either solve a generalized eigenvalue problem with LV equals dV equals lambda dV, or you can solve a standard eigenvalue problem by multiplying by d to the -1/2 on both sides. So it's just a similarity by a diagonal matrix. But yeah, everything's symmetric, and that's one of the big advantages.
Okay, thanks. One more from the chat. Are eigenfunctions of the Laplace operator shared by the Koopman operator?
Not often. I think maybe on some toruses that might be true, but typically no. So yeah, so this is a totally, so we're not, so one could imagine, let's say you want to represent this Koopman operator, right? One could imagine representing the Koopman operator in Koopman eigenfunctions, right? Of course, when you're talking about a deterministic, like if you're talking about Koopman, often you're talking about a deterministic dynamical system. And then, it may have eigenfunctions, but even if it does, there's a whole bunch of continuous spectrum So you can't really estimate that most Koopman operators that are for like chaotic dynamical systems, you can't represent those just by how they act on the eigenfunctions. So you know, you can't imagine that your Koopman operator is diagonalizable. That's typically too simplistic. Now, in this case, with the stochastic process, we do have a sort of a full measure, and so in this case, it will be diagonalizable. But we're not going to represent it in the Koopman eigenfunctions because, again, we don't know a priori what the Koopman operator is, right? And so the question really is, we want to get a representation of the Koopman operator, and so we want to minimize this error term in terms of what we can estimate from data. Yeah, so once you have the matrix representation of the Koopman operator, right? So once you get this matrix, you can then compute the eigenvectors of this matrix. And those, I think Dimitris Giannakis has shown that you can use those to estimate Koopman eigenvectors. So there are ways to get Koopman eigenvectors if that's what you're after, or at least to estimate Koopman eigenvectors. But Dimitris is really the expert on those.
Can I comment on that a little bit?
Sure, yeah, please do.
So if your dynamical systems, that is your SDEs, is also a gradient flow type, so that is that the generator is basically symmetric, then you commute. Then the eigenfunctions of a generator commute with the eigenfunctions of your geometry. So in the bigger perspective, basically what happened here is just to mimic separation of variable for solving PDE, where you have your PDE operator that has nothing to do with geometry, but then you still project it to the basis of Laplacian, eigenfunction of Laplacian on the geometry.
Exactly, yeah. So if you assume that this A is the gradient of a potential, and if you assume that the B is constant, then these will actually be Koopman eigenfunctions. Now, if you assume B is not constant, you could still treat this as a Riemannian metric, and you could actually find a new differential, you could find a new geometry where, again, you could get Koopman eigenfunctions. And yeah, John and I played around with that a while back. We found that it really didn't do too much to change the geometry, unfortunately. We were hoping to write a paper about that, but we didn't get a big improvement. But you're right, yeah. So it's sort of like a course, it's sort of like a generalization of what those eigenfunctions would be when you have non-gradient systems.
Okay, I don't have anything anymore on the audience. I'll let Novikov to take over.
I also don't have anything, so I think it's fair to close the session. So thank you, Tyrus, again for your presentation. Thanks everybody, I guess. And we have a 2-hour break till the next session. And well,
I'd like to thank all of the speakers of these sessions.
Thank you. Thank you. Thank you very much.
Right. See you guys later.